Hi, welcome back. So actually, in this episode, we're going to be doing relativistic modifications to the electron momentum equation again. I know I said last time that last time was the last momentum episode, and we were going to move on to study the thermal power of this equilibrium. However, in some of the discussions that I've been having with the community, I've realized that one of the things about this is, so it is not a two-fluid equilibrium. That's true. It's not a two-fluid equilibrium. And the problem with the two-fluid equilibrium, what prevents it from being one, are the collisions, the friction force. However, that's not a problem for this being an MHD equilibrium, which is what it really needs to be to work. And that's fine because when you add up the electron and ion momentums, those friction forces are equal and opposite. The drag the electrons put on the ions is equal and opposite to that which the ions exert on the electrons, okay? But it's still very important to consider the electron momentum here. All right, the relativistic electron momentum. And now I'm going to be clear, right, again, I'm going to be clear that this is not a full covariant derivation starting from first principles with every single level of mathematical rigor of relativistic MHD. It is simply an ad hoc heuristic appending relativistic factors where they need to be, such as in the mass due to relativistic energy increase, and also in the density due to length contraction. Because when you travel close to the speed of light at relativistic speeds, what happens is that you cause space to contract, and this is going to make the density change, okay? So what we're going to do in this episode is we're going to consider the relativistic momentum equation, or I should just say the electron momentum equation, with relativistic modifications. I'm going to show that there's a particular ordering parameter. All right, specifically, this ordering with the electron plasma frequency is much less than the Braginskii electron-ion collisionality. And if this is true, then what's going to happen is we can show that in this Z-pinch ansatz, and in fact, it might actually not even require the Z-pinch ansatz, but we'll show nonetheless that you get the ideal Ohm's law out. What the ideal Ohm's law is, again, is it's the electric field. Actually, I haven't said this before, but it's the electric field is minus U cross B. And again, we have here that U is close to UE, and that's because of relativistic electrons and stationary ions. All right, so let's write it down. Here is the electron momentum equation. All right, these are the inertial forces. Then next we have the Lorentz forces. And finally, we have the drag of the ions and the electrons, or the friction force between them, I should say. And that depends on the collisionality. So here's something that we can't do. Normally, you could say it's a collisionless plasma. We can't do that here, all right? Why can't we do that here? The reason we can't do that here is because of what this term is. It is, let's see if I can do this off the dome. This is the Braginskii. All right? The problem here is that if we said, as fusion scientists normally do, that let's just take a really high temperature, and then there'll be no collisionality, there'll be no collision frequency. We can't do that. Because if we did that, the shear of the shear structure would collapse. All right? So if TE goes to infinity, this goes to 0, so does this. And this parameter causes our equilibrium to collapse. Okay? So we can't do that. Instead, what we're going to do is, first of all, we're going to substitute in everywhere we see ME, it's going to become the rest mass of the electron times its relativistic gamma. And every time we see the density, similarly, it becomes the relativistic gamma times the proper density. So the density in the frame of the electrons, not the lab frame. And now, one last thing to say is, what is this what is this log of big lambda? This is the Coulomb logarithm, all right? This is the result of a rigorous derivation to obtain this value, and it itself depends on density. Depends specifically on what regime you're looking at. But the important thing to understand is that there's a log here, and furthermore, there's going to be a radical inside of the lambda. So on those bases, so long as gamma, which again, gamma is this value, so long as UE does not equal C, gamma will be finite, and my argument is that relativistic transformation of the Coulomb logarithm for the purposes of this heuristic derivation using ad hoc modifications, they'll be too weak compared to the gamma out front, okay? So that's my argument. Now, what happens when we do this? Okay, so what happens is we have gamma E squared, M E naught, N E naught, all right? Now we have another gamma E over here. E, gamma E, N E naught, no gammas here, okay? And then we have another factor of gamma E squared. I'm going to leave the collision frequency unexpanded for the minute. So what do we do here, right? Well, what we can do is we can say again, we can say the inertial forces are 0, but I don't want to do that actually. I don't want to do that right now. Instead of what I want to do is I want to note this. The electron plasma frequency, this is very important, is invariant. Okay? It doesn't change if you add these relativistic transformations in. All right? And the electron plasma frequency is this. So notice, if NE equals gamma E NE naught, and ME equals gamma E times the rest mass of the electron, then what we have is these gammas cancel, and we get the non-relativistic electron plasma frequency. I think that is profound. Okay? I think that's profound. So the next thing we can do, what we're going to do here is, then we're going to say that NE naught equals okay? And now we're going to insert this into here. Therefore, we have gamma E squared, M E naught squared, epsilon naught over E squared, which is the electron, the quanta of electric charge, right? Not the transcendental function E, times omega PE squared times the plasma frequency. All right. Over here, we're not going to do that. We're going to leave this NE naught as it is. But we could if we wanted to, but I don't want to. Because that's not the important term to focus on here. And it would also be misleading because realize that there's also these other small terms here. There's this small ME naught squared. Epsilon naught is pretty small. So we need to be careful about the asymptotic argument that we're making here, because that's what we're going to do. All right. So the next thing we're going to do is we've got this, that the electron plasma frequency is much less than the collision rate, okay? Therefore, the electron plasma frequency squared over the square of the collision rate is much less than 1. Right? It's close to 0. So what we need to do is we need to make sure that this omega PE squared has a new EI squared dividing into it. How do we accomplish that? We accomplish that by dividing both sides of this by new EI cubed. That's what we're going to do. And the argument for this being large is this relativistic density, this gamma, that we're at relativistic electron speeds. And so this density has a gamma out front that becomes very large. But the important thing is we cannot be at the speed of light. At the speed of light, this heuristic argument breaks down. All right? So here we have a cubed. All right. And the reason I'm not doing the same thing over here that I did over here is because we need this term. We need to retain this term. We could say that, pretty much everything here that has a plasma frequency in front of it via this density, a plasma frequency squared, could go to 0, except for the pressure. The pressure gradient is the one thing that wouldn't go to 0 by that asymptotic argument. Instead, that asymptotic argument would leave the pressure as 0, which would tell us something interesting, that this is a force, that this is a force-free equilibria. But what we really want is to study what happens to this. We want to understand what this electric field is. That's why we retain this. And I'll show you, we'll see at the end that it doesn't really matter that I'm retaining this. Okay? And then over here, we've got a gamma E squared times the inverse of the negative of the drift velocity, okay? So now, we're not quite there at the asymptotic point yet. We want to divide out a gamma e squared into everything, because that way we won't have to account for the fact that, hey, yeah, sure, these two terms might be small, or this might, this ratio might be very small. But we have these gamma e squareds that are very large at relativistic speeds. So we're going to divide those out. Divide out a gamma e squared. And we're retaining the inertial forces still, even though they disappear in the Z-pinch ansatz. And then, of course, the gamma e squared is gone from this term. And now we have what we want. We have this ratio right here. And there's no other terms in there that are going to potentially make our asymptotic argument false. We've got a very small term, another small term, and this is not large enough to overwhelm this, okay? So we're just going to take this to be about 0. And then it falls away, which is amazing. It's amazing to me that we can argue asymptotically in this heuristic derivation that even though there's tons of collisions in the plasma, even though there's tons of collisions, that the collisionality, the drag force, the friction force between electrons and ions, it goes away asymptotically, all right? And now here's the important part. Here's another thing. Then, of course, now, the next thing we're going to do is we're going to go right over here, and we're going to say the same thing, and we can do that with two different ways. We could say it's a Z-pinch ansatz. Remember, Z-pinches take care of convective nonlinearities, and they're steady. So they take care of Eulerian terms, the Eulerian derivative as well. We could say that, or we could also say it doesn't matter because this same asymptotic argument is going to kill it off anyways. So what are we left with, right? Well, again, we can say this goes to 0, and that's what I'm going to go with because that's actually much stronger in the Z-pinch ansatz. Saying something goes to 0 is much stronger than saying it's close to 0. But that's very close to 0, so we're going to neglect it. All right? And what that leaves us with then, okay, this implies that we have minus E NE naught over gamma E all right? Sorry, I'm doing my best here to write this all legibly. Okay? And this equals 0. And I mean, if you wanted to, you could probably put approximately 0. Let's say it's very similar to 0. Okay? Very close to it. And this is great because let's pull this out. That's the next thing to do, is pull out this common term of the Braginskii collisionality. And then we have just jam my knee against the wall. That hurt. Ow, that did hurt. Okay? Now here's the thing. This has a gamma lurking inside of it. The collision frequency. So it's got 3 gammas lurking inside of it. All right, I need to erase this. I need to erase some of this stuff. I'm going to leave this up here just so we know where we're at. But I'm going to erase... Maybe I shouldn't have erased those things. Oh well. Right, here it is. So what that means is that we have this relationship between the relativistically transformed collision frequency and the non-relativistic version. All right? And that's very important because as so long, I'm going to erase this now too as well, sorry, we're almost at the end here. Because so long as the relativistic gamma, which I'll rewrite it up here higher, so long as the relativistic gamma is not infinity, which only happens at UE equals C. If it's anything less than C, it could even be less than C by 1 part in a million, in a billion, in a trillion, in a quadrillion. So long as it's not exactly C, this is finite. And that means that if we go down here and we plug this in for that, what we get is we get this. One over that. Okay? So here's the great thing. We can get rid of this gamma because it's finite. For finite gamma, okay, we're going to multiply both sides by gamma e cubed. That's a 0, so they go away, which means this goes away. And therefore we have this finite value for the non-relativistic Braginskii collision frequency, right? So it's finite. We cannot satisfy this equation with the prefactor. We have to satisfy it by setting what's inside to be 0. The prefactor, there's nothing we can do here that's valid. Right? The only way that this prefactor could take this thing to 0 is if this was infinite. But what that would require is an infinite density, or it would require zero electron temperature, cold electrons, which are interesting things to think about. But we won't think about them here, because instead what we're going to do is we're going to focus on what's inside here, all right? And you can see we're almost at the end, because this implies okay? That implies that there's a force balance here. And it's oddly reminiscent, very closely reminiscent of the ideal MHD force balance. In fact, if it weren't for this electric field and these, we would have the ideal MHD force balance. Instead, what we have is we have, again, multiplying through by gamma E, we have but this gamma E just goes on top. All right? So we have something like okay? And now we cannot, I'll tell you something though, the temptation here is to say, oh, now UE equals C. We can't do that. We can't do that, because if we do that, then everything we did is invalid, because we can't move these things around like we've been doing if they're infinities. Okay? So what we can do instead is we can say, for a sufficiently large, sufficiently relativistic electrons, and it's kind of a delta epsilon thing. If you've ever studied real analysis, at that level of rigor, delta epsilon proofs are one of the first things that you run into, where there's always a real number that's greater than 0, but is smaller than whatever it is that you are thinking about. And so here, we kind of have a situation that's like that. But instead of being smaller, we can always pick a UE. However big these plasma pressure gradients are, we can always find a UE, okay, that is large enough that we can take that term to be 0. And I know the square root. I know there's a square root there, and I know that there'll be physicists saying, well, I don't know that you can say those plasma pressure gradients go to 0 slower than a square root does. Look, here's the thing, is what you're saying in that vein also has sense, something sensible to it. But that would require a very steep pressure gradient. Whereas here, what we want to study is we want to study the situation when, again, we can find that relativistic electron speed where we can take this to be 0. Okay? We can neglect the pressure gradient forces because electrons are suitably relativistic. And therefore, what we have is which implies that E has to be equal to the ideal MHD Ohm's law. QED. Thank you for watching this video. If you've made it to the end, please like and subscribe and consider donating to me. I need the support. My life, my career is about getting this research published. I came up with this problem to stump ChatGPT. It was the only out that I had was to swap the Bennett profile from number density to flow, and then study a strange limit in order to get a calculation out to stump the model with. That's what I did. And then I worked for a startup, writing a GPU pipeline, a rendering pipeline in Vulkan, reading in user data and visualizing it, and creating a clean architecture for the rest of a digital twin application for catwalk model, which is a terrible idea, by the way. If you're going to do anything that has to do with inferring the real motion of a human or another biological object, you really, this complicated macroscopic, like a mammal, you really need to use motion capture. Because anything else is going to incur a large loss of fidelity from a linear model, for example, like simple, from an uncorrelated model that doesn't capture the full depth of the non-local correlations that exist between disparate parts of the body. Like when I raise my shoulder, you might think, when I raise my arm, you might think, I'm just flexing my shoulder, right? So it's going to be local to the shoulder, what's going on, but it actually goes all the way down into the base of your back. The muscles that are involved in the stabilizing of that movement. And then after that contract ended, I've spent the last 6 months exploring this problem and putting the puzzle pieces together. So I really need your support. I do. And again, thank you for watching, and I'll see you next time.